So, what if I told you there's a kind of hidden code in numbers? You know, a language that describes everything, from how your savings grow to the way planets orbit the sun. Well, that code is built on exponents and radicals. And today, we're going to crack it wide open together. So let's just dive right in with a little puzzle.
All right, check this out. We've got a pretty straightforward pattern here with the powers of 2. I mean, we all know 2 to the 4th is 16, 2 cubed is 8, 2 squared is 4. Easy enough, right? But what happens if we keep this pattern going? What's the actual logic here? Because whatever it is, that's the key to, well, everything that comes next. So just take a quick second, look at it, see if you can spot the rule.
Okay, so that pattern you were just trying to figure out, that is our secret key. It's what unlocks the rules for dealing with the power of 0 and even negative numbers. And trust me, this is where the code starts to get really, really interesting.
So, did you catch it? It's actually pretty simple when you see it. Every time the exponent goes down by 1, the result, it just gets divided by 2. See? 16 divided by 2 is 8. 8 divided by 2 is 4. This one simple move, just dividing by 2, is basically the engine that's going to drive everything else we're about to learn.
Okay, so if we just keep that pattern going, what's next? Well, 4 divided by 2, that's 2. So 2 to the power of 1 has to be 2. Makes sense. Let's do it one more time. What's 2 divided by 2? It's 1. And boom, just like that, we've stumbled upon our first major rule. Any non-zero number raised to the power of 0 is always 1. It's not some weird math magic, it's just following the pattern.
But why stop there? Let's keep the pattern going. What happens when we divide 1 by 2? Well, we get 1/2, right? And this right here reveals the negative exponent rule. Think of a negative exponent like a ticket to the other side of the fraction line. It's super important to remember this. It doesn't make the number negative. No. It just flips its position to the denominator, and that makes the exponent positive.
All right, let's see this thing in action. Say we want to simplify 4 to the negative third power. First thing we do is use that rule. That negative exponent sends the 4 to the third down into the denominator, and the exponent turns positive. So now we've just got 1 over 4 cubed. From there, it's easy, right? 4 times 4 times 4 is 64. So our final answer is 1 over 64. Simple as that.
Okay, now it's your turn. I want you to apply that exact same logic, that flip it and solve it idea, to 7 to the negative second power. Go ahead and pause here and give it a quick try. You got it? The answer is 1 over 49. Hey, if you got that, you've absolutely nailed this rule. Let's move on.
All right, get ready for a pretty major plot twist here. You know those radical signs, right? The square roots, the cube roots, all that stuff? Well, it turns out they have a secret identity. They're actually exponents, just in disguise.
The best way to think about it is like they're two different languages saying the exact same thing. So when you see the square root of x written in radical form, it means the exact same thing as x to the power of 1/2 in exponential form. A cube root? That's just a power of 1/3. You can swap them back and forth anytime you want. They're totally interchangeable.
Okay, so how on earth do you remember which number goes where? I've got a fantastic little trick for you. Think about a tree. The roots of a tree are at the bottom, right? Well, it's the same here. The root of the radical, that little number tucked into the checkmark part, it always goes in the bottom of the fraction, the denominator. Easy, right? And that little mnemonic brings us to the core rule for all fractional exponents. Just remember, the denominator, the bottom number n, that's your root. The numerator, the top number m, that's the power you apply. So bottom number tells you what root to take, top number tells you what power to raise it to. That's the whole game. Let's work through one together. Let's take 8 to the power of 2/3. Remember the rule. We always start with the root on the bottom. So the denominator is 3, which means we need the cube root of 8. What number times itself 3 times is 8? That's 2. Okay, step 1 is done. Now we apply the power from the top. The numerator is 2, so we square our result. 2 squared is 4. And that's it. That's the whole process. Root, then power.
Okay, you know the drill. It's your turn again. Use that same exact two-step process. Root first, then power. I want you to simplify 16 to the 3/4 power. Go ahead and pause and work it out. All right, did you get it? The fourth root of 16 is 2, and 2 cubed is 8. Yes, excellent work. See, you are really getting the hang of this.
So let's take a breath. So far, we've learned all the individual pieces. We've got negative exponents, the zero exponent, fractional exponents. We've got all the tools. Now, it's time to level up and learn how to combine them to solve some much more interesting problems. Think of this as your official toolkit, your cheat sheet. These are the fundamental laws of exponents. It's pretty simple. When you multiply, you add the exponents. When you divide, you subtract them. And when you raise a power to another power, you multiply. That's it. So, let's put this new toolkit to work, shall we? All right, let's tackle something a little more complex. Take a look at this. We've got multiple things inside the parentheses, and the whole thing is raised to the power of 2. And, oh yeah, we've got a negative exponent thrown in there just for fun. This is where we have to be smart and apply our rules strategically.
The absolute key here is to not get overwhelmed. Just go step by step. First, we're going to distribute that outer exponent, the 2, to every single piece inside the parentheses. Then, for the variables, we use our power of a power rule, which means we multiply the exponents. And for the final step, we just have to deal with that pesky negative exponent by flipping the b down to the denominator. Do all that, and you've got your clean, simplified answer.
I know what some of you are thinking. You're thinking, okay, this is cool and all, but when am I ever actually going to use this? It's a fair question. So let's shift gears. Let's go from pure algebra to the vastness of outer space, and I'll show you exactly how these rules help us understand our very own solar system.
Check this out. This is Kepler's third law of planetary motion. This is a real formula that astronomers use every day. And look right there, smack in the middle of it, a fractional exponent. P equals a to the 3/2 power. This amazing little equation connects how far a planet is from the sun to how long its year is. How cool is that?
So let's go on a little mission. Imagine you're an astronomer, and you've just discovered a new asteroid. You calculate that its average distance from the sun is 9 astronomical units. Now we can use Kepler's law and the skills we just mastered to figure out how long it takes to orbit the sun. The whole big space problem boils down to one simple question. What is 9 to the 3/2 power?
So let's do it. We just apply our rule. Root first, right? The denominator is 2, so that means we take the square root of 9, which is 3. Easy. Now for the power. The numerator is 3, so we take that result and cube it. 3 cubed is 27.
And there it is. That's our answer. 27 years. 27 Earth years. I mean, just stop and think about that for a second. We just used a few simple rules of algebra that we learned today to predict the actual journey of a rock floating through space. That is the power of knowing how to crack this code.
So let's do a quick recap. Just take a look at this mastery checklist. In just the last few minutes, you have mastered these essential skills. You now know how to convert between radicals and exponents. You can handle negative exponents, you can handle fractional exponents, and you can apply all the laws to simplify really complex stuff. That is a seriously huge achievement.
So, the code isn't a secret anymore. It's yours now. And remember, these rules aren't just for calculating asteroids. They show up in finance, in biology, and all kinds of technology. So really, the only question left is, now that you have the tools, what real-world puzzle are you going to solve next?